Welcome back to Astronomy. We are in Chapter 8 on the formation of the solar system, and this video is Part 3, the age of the solar system. In this video, we're going to look at how we assess how old our solar system is. Our goals for learning: how do we measure the age of a rock, and how do we know the age of the solar system? To be able to understand how we assess the age of the solar system, how we assess the age of rocks, it's important to have a basic foundation of some nuclear physics. And so let's think about nuclei, a bit of chemistry that we started learning back in Chapter 5. And let's look at these first two. We have two isotopes, helium-4 and helium-6. Now, some isotopes are stable and some are unstable. The unstable ones are ones that are prone to falling apart. Now, sometimes it might take millions or billions of years to fall apart. Sometimes it'll take fractions of a second. But instability of a nucleus means at some point in time, it will fall apart. And I'll talk about why that is in a little bit. But different isotopes of the same element might be stable or unstable. For example, helium-4 is stable. When you have two protons and two neutrons bound together, it is not prone to falling apart. Helium-6, however, you add some neutrons and it is unstable. We have oxygen-16, which is the main isotope of oxygen that you breathe, 8 protons and 8 neutrons, and it is stable. However, if you take away a neutron, then it is very unstable for oxygen-15. I want you to notice between those two that I've shown you so far, in both examples, helium and oxygen, the stable isotope is the one that has equal numbers of protons and neutrons. Now, that isn't necessarily so throughout the periodic table of elements, but that is generally true for the smaller atoms. Now, you notice with helium-6, in adding a couple of neutrons, it made it unstable. With oxygen, it was the taking away of a neutron that made it unstable. It's beyond the scope of this course to get into determining what exactly isotopes are going to be stable and what are unstable, but you should just know that for any given element, some isotopes are stable, some are unstable, and it has something to do with the mix of protons and neutrons. Now, as the elements get heavier, such as gold that you see at the bottom of the chart, you need more neutrons relative to the number of protons to make it stable. So the stable isotope of gold is gold 197. Now, gold always has 79 protons by definition, and so 118 neutrons makes it stable. However, 117 neutrons for gold 196 makes it unstable. Why are some nuclei unstable? You got a little bit of this introduction back in Chapter 5, but let me review. It comes from the electrostatic repulsion between various particles. And remember, if you look to the chart or the picture here to the right, electrons are negative charges, protons are positive charges, and neutrons are neutral, meaning they have 0 charges. And so here's an atom with the protons and neutrons in the nucleus, and the electrons are orbiting around the nucleus there. And remember, the main rule from electrostatic theory is that opposite charges repel each other and like charges attract each other. So these two electrons, if you look over at the left, these two electrons being like charges, they repel each other. And there you can see the force arrows, they're being forced away from each other. Protons repel each other. A proton and electron, because they are opposite charges, they attract each other. And as I said back in Chapter 5, that's what makes the electrons stay in orbit around the nucleus. But let's go into the nucleus here and think about what's there. Well, there's neutrons, and they don't have any electrostatic repulsion or attraction, but you have all these protons tightly bound to each other, and all those protons are repellent to each other. And so they push away from each other. There needs to be a force stronger than the electrostatic repulsion of those protons to keep the nucleus together. So it is that repulsion that leads to instability. but it needs to be overcome if we're going to keep any atom stable. And so that brings in the nuclear strong force, which is a force much stronger than the electrostatic repulsion between protons. The nuclear strong force acts between protons and neutrons, and it is attractive. It's much stronger than the electrostatic repulsion, and it has a very short range, about 10 to the negative 15 meters. So it doesn't even act across a large nucleus. But if you look at this picture here, it will act between this proton and this proton, and between this proton and this proton, and the adjacent neutrons and protons, and it'll keep it all together. However, because of the very short range of the nuclear strong force, if the nucleus gets too large, you might have protons that are repulsive to each other electrically, and they feel no strong force attraction to each other. So a nucleus can only be so large. And as I said before, we need to have the right mix of protons and neutrons to have the proper amount of strong force that will overcome the electrostatic repulsion. Why are some nuclei unstable? A nucleus needs to have the right balance of protons and neutrons. And as I said before, it's not necessarily an equal balance, although that's usually true for the smaller atoms. Now, when a nucleus is prone to falling apart, we actually call that decay. It decays. It will decay in, there are a few different ways that it might decay. Now, let's look at one example, potassium-40. And potassium, by definition, has 19 protons, so potassium-40 has 21 neutrons. It is unstable, and it actually has too many protons. Now, nature has a way of bringing things from a high energy state, meaning the unstable state, to a low energy state, or the stable state. And you saw that back in chapter 5 when we were looking at energy levels of electrons. Nature has a way of always wanting to bring those electrons down to the lowest energy state. And stability is the lowest energy state. If you think about the stability, you build a large tower, maybe of Jenga bricks, it's very unstable. It has a high energy state, and you give it a little push and all the bricks come falling down. That's nature bringing it to a low energy state. It's more stable that way. And the nucleus is the same way. So in the case of potassium-40, it has too many protons. Now, if it had one fewer proton and one more neutron, it would be more stable. And so nature will turn it from potassium-40 into argon-40. So we say that it decays from potassium-40 to argon-40. Argon has 18 protons and 22 neutrons. And essentially what just happened was a proton got converted into a neutron. This type of decay is known as beta positive decay or beta plus decay. In beta plus decay, a proton first breaks down into a neutron and a positron. Then the positron is emitted from the nucleus while the neutron stays inside the nucleus. The resulting nucleus has one less proton and one more neutron. Now, another possibility is shown here. This is beta minus decay. An example is carbon-14. Now, carbon-14, having 6 protons and 8 neutrons, is unstable, and it has too many neutrons. So nature has a way of making it more stable, and so carbon-14 will decay into nitrogen-14. It will turn a neutron into a proton, thus making 7 protons and 7 neutrons. This becomes the stable nitrogen-14. What I've described here is beta minus decay, very similar to the previous slide, beta plus decay, but the opposite happens. In the previous slide, with beta plus decay, a proton became a neutron. Here, a neutron is going to become a proton. As it says here, in beta minus decay, a neutron first breaks down into a proton and an electron. Then the electron is emitted from the nucleus while the proton stays inside the nucleus. The resulting nucleus has one more proton and one less neutron. There are a few other kinds of decay, but I just wanted to show you those two, beta minus and beta plus, as examples. In either case that I just showed you, the nucleus changes to a more stable or lower energy state. And we say that whatever the nuclide was, think of the nuclide, that's just another word for isotope. The parent nuclide or the parent isotope became the daughter nuclide or the daughter isotope. So for example, carbon-14 was the parent, nitrogen-14 was the daughter. Let's now consider two isotopes that I showed you at the beginning of this video, helium-4, which is stable, and helium-6, which is unstable. And let's think about helium-6. Helium-6 is unstable. It doesn't have the right mix of protons and neutrons, 2 protons and 4 neutrons, but it would be more stable if one of those neutrons became a proton. And so it undergoes beta decay so that one neutron becomes a proton. Now it's got 3 protons and 3 neutrons, and it is lithium-6. Now, the reason that all of this is important for astronomy and how we assess the age of the solar system and the age of the Earth is that there's a timing aspect to this. Helium-6 has what's called a half-life of 0.8 seconds. Now, half-life is the time for 50% of a sample of a radionuclide to decay. So if you have a sample of helium-6 after 0.8 seconds, which is a very short half-life, but after 0.8 seconds, half of those nuclei will have turned into lithium-6. Another 0.8 seconds go by, and half of what was left becomes lithium-6. So gradually, all of the helium becomes lithium-6. And every radioisotope has a different half-life. But let's think about helium-6 right here. You can see in this chart, look at the top row. After 0 half-lives, which means 0 seconds have gone by, we have 100% that is helium-6 and 0% that is lithium-6 because it hasn't converted yet. Now look at the orange row here. 1 half-life goes by, and that's a time of 0.8 seconds. Now 50% of it is helium-6 and 50% is lithium-6. Let's now let another half-life go by. So now we're up to 1.6 seconds. And you can see in the third column, the percent that is helium-6, it gets cut in half. So every half-life that goes by, it gets cut in half. It started at 100%, then 50, then 25, 12.5, 6.25, and we get all the way down to 6 half-lives have passed by. Now we're up to 4.8 seconds. And we can see that only 1.563% is now helium-6. And the percent that is lithium-6 is whatever 100% minus the percentages of the helium is. So if we get 6 half-lives that have passed by, 4.8 seconds, what started out as pure helium-6 now is only 1.563% helium-6, and the majority of it, 98.437%, is lithium-6. And this brings us to the science of radioactive dating. We can determine how much time has gone by since the sample came together by the ratios of parent and daughter isotopes. Just as in the previous chart, the more time that went by, you saw that less of it was helium and more of it was lithium. So we look at, in a sample, maybe a rock sample from the moon or a meteorite that's fallen from space or the Earth, we can look at that sample and look at the ratio between how much of a parent isotope is there, how much of a daughter isotope is there, and actually determine how much time has gone by since it formed. This is a chart showing the amount of potassium-40 in a rock. And remember, potassium-40 decays into argon-40. And so it starts out, here we have on the vertical axis, it says fraction of the isotope. So that's 1. Multiply that by 100 and you think that's 100% right there. And as time goes on, the amount of potassium-40 dips down and the amount of argon-40 goes up. And so let's look right here where my marker is, right about the T of potassium-40. And it's at 75% potassium-40. And it's at 25% argon-40. And time goes on and the potassium-40 goes down in this what's called an exponential decay curve. After one half-life, which for potassium-40 is 1.25 billion years, 50% of it is potassium-40, 50% of it is argon-40. Time continues. So if you give it another half-life, which means another 1.25 billion years, this amount is going to be cut in half. So it's already down to 50%. We go another half-life, that's going to go down to 25%. And here we have, after two half-lives, which for potassium-40 is 2.5 billion years, it's down to 25% potassium-40, 75% argon-40. Now that 25%, give it another half-life, is going to get cut in half. And here we are at 12.5%. So when we investigate in moon rocks, in rocks from meteorites, we see these rocks and we see that there is a mixture of potassium-40 and argon-40. And there is very little potassium-40 in them. 12.5%, as you can see in this chart, would indicate an age for the rock of 3.75 billion years. And in fact, we find in our samples, looking at the ratio between how much potassium and argon there is, there's even less potassium than that. So we see that rocks that we find are even older than 3.75 billion years. So some isotopes decay into other nuclei. That's the parent isotopes becoming the daughter isotopes. And a half-life is the time for half the nuclei in a substance to decay. Now let's consider this thought question. Suppose you find a rock originally made of potassium-40, half of which decays into argon-40 every 1.25 billion years. All right, so I just stated the half-life right there. You open the rock and find 15 atoms of argon-40 for every 40 atoms of potassium-40. How long ago did the rock form? And so we're looking at this ratio. There's 15 argon-40 atoms for every one potassium-40. So we think about this chart right here. When the rock formed, it was 100% argon-40. And so we can think, I'm using this number 16. There's going to be trillions upon trillions of atoms, but it set it up in such a way, the question, that it was talking about 1 for every 15. And so if you looked at, let's just go to the bottom of the chart, 1 potassium-40 for every 15 argon-40. So let's just imagine we're looking at a sample, particularly of 16 atoms. Well, in the beginning, when it formed, that rock formed, all 16 of them were potassium-40. One half-life went by, and 8 of them had become argon-40. So now we only have 8 potassium-40s left. Another half-life goes by, and those 8 have been reduced to 4. And everything else, if it gets reduced, it's no longer potassium, it's now argon. So now we have 12 argon-40 atoms. And then another half-life goes by. Those 4 get reduced to 2, and the 2 get reduced to 1, and now we're left with, we see 4 half-lives have gone by, and we're left with 1 potassium-40 for every 15 argon-40s. And we can see 4 half-lives, that's a time of 5 billion years, because each half-life is 1.25 billion years. In a rock, whether it's from the Earth, the Moon, or a meteorite, scientists measure the parent-to-daughter isotope ratios to determine the age of the rock. Using a variety of isotopes with a variety of half-lives, the age estimates come out the same. Now that's a very important point. It isn't just that we're evaluating the potassium-40 to argon-40 ratio. Certainly that is a good test, but there could be a flaw in that test. So what we find in rocks is a variety of radioactive isotopes. Some of them might have a half-life of 1.25 billion years. Some of them might have a half-life of 4.5 billion years, all different half-lives. And yet, when we test them for these different parent-daughter isotope ratios, they all come out consistently to give us the same ages for the rocks. So this consistency of results gives us strong evidence for the reliability of our age estimates of the solar system. Let's do another thought question. Oxygen-15, now this is used in medical PET scans, positron emission tomography is what PET stands for, has a radioactive half-life of 2 minutes. If you start with 40 milligrams of oxygen-15, how much will be left after 6 minutes? And so it gets cut in half every 2 minutes, and you start with 40 milligrams. Now, as we look at these possibilities, there's one that you can immediately get rid of. Immediately get rid of option A, 80 milligrams, because that would be an increase in the oxygen-15. It's not going to increase, it's only going to decrease. So we can get rid of option A, clearly not the right answer. But let's think about how to work through this. It has a half-life of 2 minutes, and if we started with 40 milligrams, then after 2 minutes go by, it's cut in half. You're down to 20 milligrams. After 4 minutes go by, so that's another half-life, that 20 gets reduced down to 10. Let's give it another half-life. After 6 minutes go by, and that's what the question is asking about, after 6 minutes, that 10 has been reduced to 5. So what we see is that 3 half-lives have gone by. 6 minutes, 2 minutes apiece, so 3 half-lives have gone by. And in 3 half-lives, you cut the amount in half, then in half again, then in half again. You're basically dividing it by 8. And so we're left with an answer of 5 milligrams. And by the way, the other 35 milligrams that has disappeared, it hasn't just vanished, it's actually become another isotope, a more stable isotope. An application of all this is nuclear medicine and medical physics. Nuclear medicine uses radiation to provide diagnostic information about the functioning of a person's specific organs or to treat them. And then there is radiotherapy that's used to attempt to heal the body. It can be used to treat some medical conditions, especially cancer, using radiation to weaken or destroy particular targeted cells. Before I was a physics and astronomy professor, this is what I did in the Army. I worked in nuclear medicine. I was a medical physicist, and I worked with these things. And so, for example, we used iodine-131. It has a half-life of 8 days. Now, in nuclear medicine, we're not going to use isotopes that have half-lives, long half-lives like years, certainly not billions of years, because if we put it in the patient's body, we want it to disappear. We want it to do its job and then disappear as soon as possible. So the nice thing about short half-life radioisotopes in nuclear medicine is it goes away before long. It all disappears. It all decays. So iodine-131 has a half-life of 8 days, and it's used for diagnosis and treatment of thyroid cancer. Thallium-201 has a half-life of 73 hours, and this is used often by cardiologists to do what's called a nuclear stress test, where they inject it into the body, into the blood, and the radiation that it gives off actually can be picked up by cameras to map out the flow of the blood inside the body. And then, as I mentioned previously, oxygen-15, very short half-life of 2 minutes, is used in PET scans. So now let's bring this all to estimating the age of the solar system. Radiometric dating tells us that the oldest moon rocks are about 4.4 billion years old. And again, we use a variety of radioactive isotopes to do that test, and there's a pretty good consistency that the oldest moon rocks we found are 4.4 billion years old. The oldest meteorites are found to be 4.55 billion years old. So we've got these rocks from completely different sources. One is from asteroids that are, these rocks that are in orbit around the sun, and another is from rocks that were actually picked up from the moon and brought home. And they both show great consistency, having formed about the same time, about 4.5 billion years ago. So we estimate that the solar system and the planets probably formed about 4.5 billion years ago. Now also keep in mind, let's have a broader perspective here, this is not referring to the age of the galaxy or the age of the universe. We have other methods for assessing those, but we are right now just talking about our solar system, our little neighborhood in space. The universe is estimated to be much older than the solar system, about 13.7 billion years old. And towards the end of the semester, when we study galaxies, when we study the universe, the large-scale structure of the universe, we'll get into how we assess the age of the universe and the size of the universe. And so if you think about a timeline of the universe, here we are on the right, present day, but let's go back to the moment of creation. So here is what we call time equals 0, when the universe started. And then we estimate that galaxies started forming or were formed when the universe was about 1 billion years old. And again, when we get to studying galaxies, we'll get more into why we think that is true. And I want you to see as we're going along the timeline, we're still far to the left right here. But so very, very early on in the universe, galaxies, including our own, formed. And then many, many billions of years went by, and our solar system formed about 4.5 billion years ago, which means when the universe was about 9 billion years old. And you look at that huge gap between the creation of the universe, creation of our galaxies, how much time went by before our solar system formed. And when we get into, in the next unit, studying stars, you'll see why all this time, it wasn't just a waste of time, but rather the universe and our galaxy were getting ready as heavy elements were created inside stars, the elements necessary for planets, the elements necessary for life. They were slowly being created inside previous generations of stars, so that the galaxy was ready for us, for our solar system. But it took several billion years process to get it ready. And so when the universe was about 9 billion years old, our solar system formed and the planets formed, and then about 4.5 billion years pass, and here we are today in the present, with the universe having an age of about 13.7 billion years. So in this video, what have we learned? How do we measure the age of a rock? Some isotopes decay with a well-known half-life. Comparing the proportions of those isotopes with their decay products, remember that's the parent isotopes decaying into the daughter isotopes, that tells us the age of the rock. How do we know the age of the solar system? Radiometric dating is what we use, and it indicates that the planets formed about 4.5 billion years ago. That is the end of part 3, the age of the solar system. Have a great day.